Welcome back to the course on mechanical behavior of materials part 2. So in the last lecture, we covered the topic on toughening in ceramics. Today we will talk about fracturing polymers. Okay. So I've listed here some of the general properties for polymers as compared to metals and ceramics. So strength, hardness and modulus, those are lower for polymers as compared to metals and ceramics. And as far as application temperature is concerned, that is also lower for polymers uh, as compared to metals and ceramics. Okay. So here I am showing a plot of specific volume versus temperature. Okay. So you have three different materials: crystalline, amorphous and glassy polymers, and semi-crystalline polymers. Okay, or materials in general, any materials. Okay, and if you see how the specific volume varies with respect to temperature, you will see that for crystalline materials, as soon as it crystallizes, there is a discontinuity in the specific volume at melting temperature Tm. Okay, and that is shown in the red plot here. So if you just lower it down, it is coming down the specific volume with respect to temperature, and at melting point, you have a discontinuity because of the melting. Okay, so that is how a crystalline material is going to behave as you lower the temperature. Now the second is amorphous and glassy polymer. So when we say a material is amorphous or glassy, it means that there is no long range ordering, will exist in that particular material. Now, second characteristic is that the material is going to exhibit glass transition temperature, but no melting point. As such, there will be no melting point, but it is going to exhibit something called glass transition temperature, below which your material is going to be rigid, okay, and above which it is going to be viscous, and finally it will be converted to liquid, obviously. Okay. So that is what the black curve here is shown. So below Tg, which is this region here, you have glass and amorphous. And then between Tg and Tm, you have supercooled liquid. It is sort of viscous. It is neither liquid, neither solid. And above that, you have a liquid. And semi-crystalline polymer, the last category, it is going to behave between the amorphous and glassy material and crystalline material. So it is going to exhibit both, okay, glass transition temperature as well as melting temperature. So crystalline part is going to, behave towards the crystalline material behavior, and the amorphous part of the semi-crystalline polymers, they are going to show the behavior shown by typically amorphous and glassy materials. So you are going to observe two behavior here, right? So if you see the blue one at Tm, you are going to see a drop, as well as there will be change in Tg also because of the amorphous characteristics in semi-crystalline polymers. Okay. Now, based on the behavior upon heating, polymers can be divided into two categories. One is thermosetting, another is thermoplastic. So thermosetting polymers, in these type of polymers, molecules are highly cross-linked in the form of a network. That means when you heat it, they are not going to soften, okay, because of the highly cross-linked nature of the molecules. Now, cross-linking makes sliding of these molecules very difficult, and that's why these thermosetting polymers are slightly stronger as compared to the thermoplastic polymers. Okay. Examples are vulcanized rubber, epoxy, phenolic, polyester, silicone, etc. Now, thermoplastic polymers, on the other hand, if you heat it, they are going to soften and eventually they are going to melt. Okay. Remember, thermosetting polymers, they are going to not melt, they are going to decompose if you increase the temperature. Okay. So examples of thermoplastic polymers are low and high density polyethylene and PMMA. Okay. There are many examples of thermosetting polymers and thermoplastic polymers. And depending upon the heating, we have divided into two parts. Okay. Now, these polymers in general can have amorphous or partially crystalline structure. It is very difficult to get completely crystalline structure of polymers. Okay, and now we know what is the difference between an amorphous or glassy polymer and the another category, partially crystalline structure, that we have discussed. Partially crystalline structure is similar to the semi-crystalline polymers. Okay. So thermosetting polymers such as epoxy, phenolic, unsaturated polyester, typically they are going to exhibit amorphous structure, whereas thermoplastic polymers can have both amorphous as well as semi-crystalline structure. Okay. Now let's understand how modulus of polymers vary with respect to temperature. So now here I have shown the plot for glassy polymers. Okay. So y-axis is modulus and s-axis is the normalized temperature with respect to Tg. Okay. So 1 here represents Tg. Okay. So glass transition temperature. So above 1, you are going to have amorphous structure, right? That means your material is going to be stiff. Okay. It is so that means modulus is going to be higher. And as you increase the temperature, it is going towards the viscous nature. And finally, it will be converted to melt. Okay. So that's why you see a decrease in temperature, decrease in modulus with increase in the temperature. Okay. So that's what I have written here. So above Tg, modulus is low and behavior of the polymer can be described as rubbery and viscous. Okay. Which is this region here. Okay. Below Tg, modulus of elasticity is higher. Okay, and it is close to the linear elastic below Tg, and you will see the stress strain behavior in the next slide, where you will see that below Tg polymers are going to behave like a brittle material. It will show the elastic behavior. Okay, and then you are going to obviously have a gas transition temperature. There also, as you increase the temperature, you are going to observe a decrease in the modulus value. Okay. Now, what are the stress strain behavior of polymers? So we can have brittle polymers. Okay, we can have ductile with or without necking. So the top one here is without necking. And the second one, this one is the necking, right? So here you are going to observe formation of necking. Okay, and then the curve goes down, it flattens and then again increases. And this can be ascribed to the untangling and the alignment of the polymeric chains. Okay, and the last one is your elastomers, which is typically we observe for rubbers. Okay, so in general, thermosets polymers, especially below Tg, are brittle in nature. Why? Because they are highly cross-linked. So it is very difficult to align the chains, right? So thermosets polymers in general are going to show you brittle nature, which is the black curve here. Second, the glassy and semi-crystalline polymers, right, below Tg. So semi-crystalline polymers and the amorphous polymers below Tg, they are going to be rigid. We have discussed that, right? That means they are going to show the black curves, the behavior of the black curve. So if you do a tensile test, it is going to show you a linear elastic region, predominantly linear elastic region, and then it is going to fade. And it is especially valid for polymers having a large and bulky side group or having a high density of cross-link. Either of these two. Okay. Now the red curve here, these are for ductile polymers. So it can be with necking and without necking. So the with necking one is typical characteristic of semi-crystalline polymers. Okay, and the top one, if we increase the temperature of a glassy polymer and we go nearby, TG, it can show a ductile behavior. Okay, remember the brittle behavior is typical characteristic of semi-crystalline and amorphous below TG. And the last one is for elastomers, especially for rubbers. Okay, so typically you can observe the stress strain behaviors of the polymers like this, depending upon what type of polymers you are using and depending upon what is the temperature. Okay, if it is below TG, you are going to observe brittle behavior. Okay. Now let's talk about how it deforms. Okay, and there are two phenomena. You will go through bits and you will see a concept of crazing and shear yielding in glassy polymers. Okay, so let's understand what are these two. So similar to the metals, plastic deformation can also occur inhomogeneously in polymers. Okay, so in metals, we know plastic deformation can occur inhomogeneously, right? Especially after making. Similarly, in polymers, you can get inhomogeneous plastic deformation. Okay, and when that happens, you can have crazing and shear yielding. Okay, so crazing and shear yielding, and sometimes many books will refer shear yielding as the formation of shear bands during shear yielding. Okay, and after that, it is going to fail. So before fracture, you are going to observe these two phenomena depending upon the polymers you are going to have. Okay. So what is shear yielding? So in the process of shear yielding, you are going to observe shear bands at about 45-degree angle, okay, to the largest principal stress. That is point number one. In the shear band, the polymeric chains are going to align and there will be no change in volume. And this is the major difference between shear yielding and crazing. You will see that. That is point number two. Third, shear band formation requires some energy, and that means it can increase the polymer toughness. Okay, point number three. And shear yielding you are going to observe in those type of polymers which are more ductile in nature. Okay, where you can have polymeric chains can be flexible. Okay, so there you are going to observe shear yielding rather than crazing. So what is crazing? So craze, it's a region in a polymer in which normal crude spaghetti-like chain characteristic. Okay, so you have a characteristic like this, say that is a chain spaghetti-like. So they are going to arrange and become something like this. So this type of structure is called crazing, and that is what I have written here, right? So the spaghetti-like chain arrangement, which is a typical characteristic of amorphous state, right? They have been transformed into a drawn out molecular chain. Okay, so you have a molecular chain like this, and then you have voids in between. So these are your voids. So this is craze. Okay. So overall, if you see the bulk polymer, a trace region is going to be very, very small percentage of the total polymer, and they will occur in a narrow range. That is another characteristic of crazing. Okay. Now, since there is a presence of voids, and as I have shown here on the right side, the schematic, the plastic deformation of small volume of material in a trace occurs without a lateral contraction. Typically, it is going to increase the local volume. Okay, that means consistency of volume condition doesn't hold in trace, whereas it can hold in shear yielding. Okay, that is point three. The last one is the trace is neither a void nor a crack. Okay, remember trace is not a crack and it's not a void. Okay, it's a molecular chain which is, it's a region where the molecular chains are aligned and in between you have voids. And typically the void content is going to be 50 to 55% by volume. Okay, that means density of the trace region. So if you have a bulk polymer, okay, and suppose you have a trace region here, trace regions are going to be typically perpendicular to the stress axis. Okay, so if this is a trace region and if you just see the density in the trace region and away from the trace region in the bulk polymer, the density of the trace region is going to be lower because of higher percentage of voids, which is typically 50 to 55% of volume. Okay. So let's see some of the images of the trace. So this is a paper from 1987, Crazes and Fractures in Polymers. And you can see, so these lines here, right, white lines, these are traces and these are typically perpendicular to the loading axis, right? Okay. So here also you have traces, but very, very fine traces. So you see it happening over the dead session. This is a TM image of crazing. Okay, so this is how trace look like in a polymer. So traces are not rafts, I mentioned, right? And these are not voids. Voids are the part of the trace, right? But trace can help in crack propagation and initiation of the crack, which can lead to the final fracture. So if you see the right schematic here, right? So you have a crack which is this. These are your tangled or say spaghetti-like chains. And what you see here in the region between the track and spaghetti-like structure, this is your crazed region where the molecular chains are aligned and in between them you have voids. Okay, so these regions is your crazed region. Okay, now if you have sufficient amount of stress, the track can easily propagate to the trace because trays have 50 to 55% of voids, right? Okay, so if you see this, when we have sigma here, trays in the trace, the molecular chains are getting aligned. That is what we also discussed previously. Okay, so let's see more about tracing, especially schematic and figures. So you see, this is a track here, the white region, okay, up to this particular point. And what you see here, these lines, these are your trace regions. So you have voids as well as you have polymeric chains which are aligned. Okay. Now this track is going to propagate after breaking those polymeric chains. Okay. Here also you have a track and then this is a traced region and you have bulk polymer. So the track is going to propagate through breaking of these chains. Okay. And you can see here, this is what the track is now after breaking the chains. Okay. Now second paper. So this is by mechanical properties of solid materials. Okay. And if you see here, so this is the trace region and then, you know, the polymeric chains are broken and then crack propagates. The last one here. So you have a crack tip here, the black region, and then this is the trace region here, right? So these are your voids, the black one, and the shaded region here are your polymeric chains. Okay, and if you have sufficient amount of stress, these polymeric chains are going to break, and thereby your crack is going to propagate. Okay. Now the last topic is, you know, the fractography. If you see the fracture surface of the brittle fracture of polymers, you are going to typically observe three regions. Okay. So first is smooth mirror, etel, and mist. And I've shown here the schematic on the right side. So this is the origin of the brittle failure. After that, you see a flat surface. Okay. very smooth surface. So we call this region as smooth mirror. Let me highlight. So this region here, okay, this is your smooth mirror region. Next, you have a mist region, this dotted line. No resolvable features are there. Okay, but this is the region which separate smooth mirror region and Hetel region. And the last one here I have shown, this is your Hetel region. So they are typically three regions. Okay, smooth mirror, mist and Hetel region. And origin you will be able to observe if you see the pattern. Okay, so smooth mirror is a mirror-like region as joining crack nucleation site. So this is your crack nucleation site origin, and then you see a smooth mirror region adjacent to that. So that is your smooth mirror region, and it typically indicates that crack growth is slow. Okay, Heckel, it's a coarser and flat region indicative of fast crack growth. So these lines here, right? So these will indicate that the crack growth is faster, and you can clearly see the crack has propagated on different levels over this small area. Okay. The last one is the mist, which is a transitional region between smooth mirror and the Heckel region. And it has a misty appearance, and you will not be able to resolve any feature. Okay, so let us see some of the images of this surface, fracture surface. So this is in composite part B 1999 by Liao. And if you see, yeah, here. So you can see a mirror type region. So somewhere here the crack might have nucleated, correct? So you have mirror type region, and then in between Hethel. So this is the Hethel pattern, right? So in between you can see a little region, which is the mist region. Okay, so this is how your fracture surface of a brittle fracture of a polymer is going to look like. Another image for the fracture surface here. So see, you can clearly see this is the indication of the initiation, right? Origin. Then you have the mirror. Okay. Then you have the mist region in between the head tail and the mirror, and this is the head tail region. Okay, very nicely it shows the three different regions, okay, in a brittle failure. So overall, if what is the major difference between the crazing and shear yielding? Okay, so the first is the crazing occurs with increase in the volume, and shear yielding occurs at constant volume. So you can apply the consistency of volume in shear yielding. Second, in less ductile polymer, the crazing phenomena is going to be dominant. However, in more ductile polymers, shear yielding is going to be dominant. Okay, so both are again localized deformation, but depending upon the nature of the polymer, the dominance of the crazing will be observed in less ductile polymers, and shear yielding is going to be dominant in more ductile polymers. Okay, so I will stop here. Thank you.